12 এর সেই অংশটা আমরা দেখো আজকে আলোচনা করব। ডেরিভেটিভের শেষ অংশে রয়েছে সেকেন্ড অর্ডার ডেরিভেটিভ, ফার্স্ট অর্ডার ডেরিভেটিভের মাঝামাঝি একটা অংশতে দেখো রয়েছে, সেটা হচ্ছে রোলস থিওরেম অ্যান্ড ল্যাগ্রেঞ্জ মিন ভ্যালু থিওরেম। তো এই যে দুটো থিওরিম পড়া আছে এবং এই দুটো থিওরিমের প্রুফ তোমাদের নেই ঠিকই, কিন্তু এই দুটো থিওরিম তোমাদের ভীষণ ইম্পর্টেন্ট, কারণ এখান থেকে প্রতি বছর অঙ্ক থাকবে, কোনো একটা ফাংশন থাকবে, সেই ফাংশনটা রোলস থিওরিম বা ল্যাগ্রেঞ্জ মিন ভ্যালু থিওরিম স্যাটিসফাই করছে কিনা সেটা তোমাদেরকে ভেরিফাই করতে দেবে। তো আমরা এখানে রোলস থিওরিমটা নিয়ে প্রথম আলোচনা করব, তারপর ল্যাগ্রেঞ্জ মিন ভ্যালু থিওরিমে যাব। তো রোলস থিওরিম কি, রোলস থিওরিমের স্টেটমেন্ট কি, সেটা আমরা প্রথম দেখে নিই এবং সেটাকে কিভাবে আমরা প্রুভ করতে পারি সেটাও দেখে নিই। সো এই যে ক্লাসটা আমরা করতে যাচ্ছি রোলস থিওরিম, তো সেটা ক্লাস 12 অ্যান্ড হায়ার ক্লাসেস অফ ম্যাথমেটিক্স ভীষণ ভীষণ কাজে লাগবে, তাই জিনিসটা একটু মন দিয়ে তোমরা কেয়ারফুলি শুনবে। তো লেট আস প্রসিড। Let a function a from a b to r such that condition 1 fx is continuous on the closed interval ab. Number 2, fx is differentiable at every point of the open interval AB, and the third condition, value of the function at the point x equal to a and value of the function at the point x equal to b are equal. So, if a function f defined on the closed interval AB, real valued function, such that the following conditions satisfied by the functions. The first condition, condition 1, the function must be continuous over the closed interval AB. Condition 2, the function is derivable, that is differentiable over the open interval AB, that is f dash x exists over the open interval AB, and the value of the function at the point x on a and the value of the function at the point x equal to b are equal to each other. Then there exists a point xi in between a and b, that is a less than xi less than b, such that f dash xi equal to 0. That is the result of Rolle's theorem, the statement of Rolle's theorem. Now we proceed to proof of this theorem. Proof. Since the function is continuous, the first condition, since the function is continuous over the closed interval AB, so it must be bounded here. Since the function fx is continuous over the closed interval AB, so it must be bounded. And attains its bounds. By the property of continuity. Not only bounded, it must attain its bounds, that is, there must exist two points C and D such that f of C equal to the maximum value of n and f of D equal to the minimum value of n. Let soup of fx equal to n over the closed interval AB and the inf of fx equal to small n over the closed interval. If is taken over the closed interval AB, that is x belongs to n. That is the supremum of fx is equal to n and minimum of n. Then by the property of property of continuity, there exist points C and D such that f of C equal to n and f of D equal to small n. C and D must belong to this closed interval AB. So that is by the property of the continuity. So finally, these two numbers, that is the supremum and the infimum of the function f over the closed interval AB. Two cases may be arise. Either these two values equal or distinct. The first case we consider. So two cases may arise. Case 1. Let us consider n equal to m. There is a supremum and the infimum value of the function are equal. Then obviously fx equal to n for all x belongs to AB. So the function is constant over the closed interval AB, and derivative of the constant function is always vanishes. And so f dash x equal to 0 for all x belongs to AB, and the theorem holds trivially. And the theorem holds trivially in this case. That is m equal to n. Next, another case. Now we consider n not equal to small n. Then what happens? If the supremum value of the function is distinct from infimum value of the function. Case 2. Let n not equal to n. In this case, at least one of n and n, if not both, must be unequal to the f of A and f of B. So what we write here? To write if m and m are distinct, that is the sup and m are distinct, then at least one of m and n, if not both, must be unequal to fa and fb. Let n not equal to fa. At least one of m and n must be unequal to fa and fb. So consider m not equal to fa. What is m? Now m is the value of the function at the point x equal to c. That is fc equal to m. So c not equal to a and c not equal to b. Why? Because n must be unequal to fa and fb. So c not equal to a and c not equal to b, then it is a less than c less than b. That is a less than c less than b. And the second condition of Rolle's hypothesis states that the function is differentiable at every point of the open interval AB, over the open interval AB. Therefore, f dash x exists. F dash c. Therefore, f dash c exists because c lies between the open interval AB. C belongs to the open interval AB. So f dash x exists, and f dash c equal to limit extends to C, fx minus fc divided by x minus c. From the definition of the derivatives at the point x equal to c. Now let if possible, f dash c greater than 0. We want to prove f dash c equal to 0. Then the theorem is proved, because there exists a point xi in between a and b such that f dash xi equal to 0. That is the conclusion of Rolle's theorem. So we want to prove f dash c equal to 0. So if possible, let f dash c not equal to 0. Then it is either greater than 0 or less than 0. Let if possible, suppose f dash c greater than 0. Then what's happened? Now limit x tends to c, fx minus f of c divided by x minus c, that is greater than 0. This limit is greater than 0. So there exists a positive delta. Such that fx minus f of c divided by x minus c, that is greater than 0 for all x belongs to c minus delta comma c plus delta. That is the neighborhood, delta neighborhood of c. In delta neighborhood of c, fx minus fc divided by x minus c must be greater than 0. Therefore, fx minus fc greater than 0, fx minus fc greater than 0 whenever c less than x less than c plus delta. The full neighborhood, that is here c minus delta and c plus delta, if x belongs to this, here is x, that is c delta neighborhood of c minus delta and c plus delta. Here c less than x less than c plus delta. That is x greater than c, that is x minus c greater than 0. If x minus c greater than 0 and fx minus fc greater than 0, so the numerator must be greater than 0, and therefore fx minus fc greater than 0 whenever c less than x less than c plus delta. That is fx greater than f of c. And what is fc? fc equal to m. And what is m? M is the supremum value of the function. So fx greater than m, according to the definition of supremum, so that is the greatest value of fx over the closed interval ab, that taken by x. So fx, the x which includes here does not satisfy fx greater than n, because n is the supremum value. So it is a contradiction. That contradicts the result. That contradicts the statement that n equal to sup of fx. That is the supremum value of fx. So how fx greater than n? So this is a contradiction, and this contradiction states that f dash c, which we here it is. Let if possible f dash c greater than 0, our assumption. According to this assumption, we arrive fx greater than the supreme value of x. So it's a wrong, and this wrong is happening because we assume f dash c greater than 0. So this contradiction states that f dash c must not be greater than 0. Okay, let f dash c less than 0, then what's happened? Consider if possible let f dash c less than 0. Then what's happened? Then limit x tends to c fx minus fc divided by x minus c, that is less than 0. That is less than 0. And fx minus fc, therefore fx minus fc divided by x minus c, this is less than 0. It's a wrong. As it is less than 0, so there exists a positive delta. So there exists a positive delta such that fx minus fc divided by x minus c, that is less than 0 for all x belongs to c minus delta comma c plus delta. Within delta neighborhood of c, fx minus fc divided by x minus c less than 0 because the limit less than 0. Just concentrate here. That is c minus delta less than x less than c plus delta. Then we conclude fx minus fc greater than 0. How? How the numerator is greater than 0? Now then, the denominator must be less than 0. When? Now when you are the denominator x minus c less than 0, then x must be less than c. So c minus delta less than x less than c, that is x less than c. So x belongs to c minus delta and c, which is c minus delta and c, and therefore fx greater than fc and fc equal to n, and therefore fx greater than n, which again a contradiction because n is the supreme value of fx. If n is the supreme value of fx, then how fx greater than n? So here is a contradiction. This contradiction. So again we arrive at a contradiction. So this contradiction proves that our assumption is wrong. That is, our assumption is f dash c less than 0. So f dash c must not be less than 0. So our target is f dash c equal to 0. First we suppose f dash c greater than 0. Then we arrive at a contradiction and we conclude f dash c must not be greater than 0. Again let another condition, f dash c less than 0. And again we conclude that f dash c must not be less than 0. So these two conclusions suggest that f dash c must not be greater than 0, f dash c must not be less than 0. Then what is the value of f dash c? Then there is nothing to say that. Conclude that f dash c must be equal to 0. F dash c must be equal to 0. So we find a c. So we find a c that is j equal to c such that f dash j equal to 0 where a less than b, here j equal to c. So find the value of j in between a and b such that f dash c equal to 0. So case 2, in the case 2, we also prove that there exists a point c within the open interval ab such that there exists a point j within ab such that f dash j must be equal to 0. Now, in the case 2, there is another part. In case 2, we assume. In case 2, we first assume n not equal to fa. And then, after that, f dash c greater than 0. Then we prove that is not greater than 0. Next, we assume f dash c less than 0. We again prove that not less than 0. And these two simultaneously suggest that f dash c equal to 0. So there exists a point j, that is c, such that f dash j equal to 0. So in our part 2, that is in case 2, we assume f not equal to fa. So there is a case such that f equal to a, it may be equal to a. So if a is equal to however, so if however a is equal to a, then as n not equal to n, then as n not equal to n, but n equal to fa, so n must not be equal to fa. That's a great conclusion. As soup and imp are distinct, in the case 2, soup and imp are distinct, and soup, the value of the supremum equal to fa, then n, the small n, that is the infimum of fx must not be equal to fa. And from this, we conclude that the value n taken by a at the point x equal to d. So d must not be equal to a and d must not be equal to b. Why? D must not be equal to a because n is the value of fx at the point x equal to d, at the point x equal to d, that is fd. So fd not equal to fa, so therefore d not equal to a, and fa equal to fd, so d must not be equal to b. So d must enter in the open interval. So d must enter in the open interval a and b. And proceeding as above, considering f dash d, that is this d, considering f dash d greater than 0, f dash d less than 0, and we prove similarly not greater than equal to 0, not less than equal to 0, and therefore f dash g equal to 0. So similarly we prove that f dash d equal to 0, that is there exists a point j in between a and b such that f dash j equal to 0. And the theorem of Rolle's theorem is complete. Proof of the Rolle's theorem is complete. Just a synopsis this total result. Now, what is the theorem statement? The statement is that if a function f from a b to r Condition 1, the function is continuous over the closed interval a. Condition 2, the function is differentiable at every point on the open interval a b, and f a equal to a b. Then there exists a point j in between a and b such that f dash j equal to 0. We first consider n not equal n equal to n. That is, n is the sum and n small n is the in. Since the function is continuous over all the closed interval a b, therefore it must be bounded and it attains its bound, so it must take the value of sup and in. So there exists a point c and d such that fc equal to capital M and fd equal to small m. And considering m equal to m, we prove that f dash x equal to 0. And considering m not equal to n, we also prove that f dash there exists a point j such that f dash j equal to 0. So in every case, we must find a point j in between a and b such that f dash j equal to 0. That is the result of Rolle's theorem. So you must learn this theory and follow this theory. And this is a very important theory and very much applications in our higher mathematics. Thank you.